Yeah. So I'm very sorry for being late for second like the event of the seminar. I just fell asleep and let me do a bit short, but also still cover the core of the material of the complex geometry. So what I wanna do today would be the following. So may probably by next like the seminar, my original intention was by next seminar, I'd like to make the rigorous statement of the Calabi conjecture, which might be the most important like the statement of complex geometry. So the goal is to understand this statement. So our goal is to understand the following statement. So this statement is usually called by Calabi conjecture, but this was already solved in 1978. So rigorously, we should say this is Calabi-Yau theorem, solved by uh, Sing-Tong Yao. So the statement looks a bit abstract. So we start from compact Kahler manifold without any further assumption. And nowadays, the extension of this theorem is there are lots of variations so that we do not need to require compactness. We do not need to even require the Kählerness and so on. But this is still I think, the most important, like the concrete, like the statement that one need to understand for the various versions. So we choose, so from here it could be abstract. So we choose the row from so-called the first chunk class that I need to explain what this is. So, and because of the scaling, one usually multiply by 2 pi and choose the element from here. I think I should explain what this rigorously really means, but once you figure out this is what exactly we need. So this element, this 2 pi C1 first chunk class. So this is also one of the element inside of the second drum cohomology class. And in this case, I should write this guy as a actually MR, real valued like a coefficient. So this is actually any so-called a real one-on form. This real corresponds to this choice. And this one-on form, I think I also need to explain. So this is the only given condition in the Calabi conjecture. So given we are one-on form, then what we'd like to claim is that then unique, we are able to find unique Taylor metric omega, omega, such that, so this are, let me just mention this just precisely, such that the drum cohomology class of this omega is same as drum cohomology class of the initial Kähler metric, and and the Leach form of this omega is equal to rho. So this is the statement that I think in order to study complex geometry, one must understand what this statement really meant. So the purpose of the seminar for today and probably by next time is to spend our like the energy to understand what each of the like the objects and the definitions if necessary, and review for the necessary like the materials to just understand this statement. And in order to understand what this is, so let me start from probably the review of, let me say, Kähler manifold. So if you study already Kähler geometry, then you are definitely already know it. But if you just study several complex variable, most of the time you just look at the bounded domain in Cn. So that in that case, the Kähler-ness is familiar like the terms, but still I think we need to figure out together. So in order to talk about this condition, so we first need to mention there are several objects M. M is basically smooth manifold. Of course, one can weaken the regularity, but we usually assume just a smooth manifold. And there's a so-called the complex structure. And we also have this connection. So this connection is called the Chern connection, which is usually different from the Levi-Civita connection. But in the case of the Kähler, this is same as the Levi-Civita connection. And there is so-called the Kähler metric. Birdie, I'm very sorry for being late for today. I just fell asleep and couldn't just wake up. So I'm sorry.
Ah, it's okay. It's okay. Nice.
So my original intention for today's seminar is that I just wanna pick up the probably one of the most important like the statement of the complex geometry. This is the Calabi conjecture, and I didn't intend to cover all the details for today, but I just wanna list of the objects that we need to understand together. So let me just mention from the beginning again. So by probably by next time, we'd like to understand the following statement of the Calabi conjecture, which was already solved in 1978, so that we need to call it by Calabi theorem, but most of the people still call it by the Calabi conjecture. So the statement is, so we have the compact Kähler manifold, and I think I need to explain what is the first chunkless, but we choose the first chunkless times 2 pi, and we just take one of the representatives, say rho. So first chunkless also should be the element of the second term cohomology class. So that anyhow, we just choose one of the representative as a so-called the real one-on form. And for the participants, I don't assume they already have the necessary background to understand what this really means. But so this is what I think I need to explain. But this is a given input of this conjecture. Then the Calabi conjecture states that there exists unique Kähler metric omega. This is omega is different from the initial Kähler metric omega naught. So omega and omega naught, they are the same in the second term cohomology class, and the rich form of the omega coincide with this rho. And this rho was the arbitrarily representative from the 2 pi of the first chunk class, and we can always induce the Kähler metric uniquely. And in order to understand this statement, I think it's safe to start from really the beginning that we need to just look at each of the objects in the Kähler manifold. So there are essentially four necessary objects that we need to just review. One is a smooth manifold, but I don't think I need to explain what is a smooth manifold. You already have the definite background for, I mean, all of the participants here. And the complex structure, this now makes distinction from the basic, the usual differential geometry to the complex geometry and also the world of the symplectic geometry. So I think we need to start from the complex structure. And the Chern connection is required, but in the case of the Kähler manifold, so it's just nothing but the same as a Levi-Civita connection. So if you already had the experience of the calculating the sectional curvature, then I will simply just assume we just have the Levi-Civita connection and proceed the calculation. But actually, it requires the explanation what is the Chern connection. But so if it's such a case, also let me know. And the Kähler metric. So this is one of the special Riemannian metric, but the this is a bit weird in a sense that this is real two form. So that if you just don't know the Riemannian geometry, this looks a bit strange that we always represent the Riemannian metric as so-called the symmetric to tensor, whereas the Kähler metric we usually meant is the real differential two form. So that there are some distinctions that we need to clarify why we need to choose some different like the convention compared to the usual Riemannian geometry. So let's from indeed the beginning, if you do, the guys do not mind. But do you have any good questions so far? So any like the suggestions or opinions up to here? So if not, let me just continue. So first, we have a complex structure. So I think the one of the most like the famous open question first, because this is sort of the also research conversation. So open problem, you might heard about the following. So show that six-dimensional sphere does not admit the complex structure. Does not admit the complex structure. So this is very famous classical, like the open question. So before Professor Atia passed away, he tried to solve this, like the conjecture, and he tried to post some like the his preprint on archive, but it was completely incorrect. So he did it in my memory around the 2016. So still, this is one of the very classical question. So, but anyhow, so the complex structure requires the smooth manifold first. So we have a smooth manifold. Then the complex structure means that we start from the almost complex structure. So we have, if you have so-called a bundle endomorphism, usually denoted by J. So this is still the map from the real tangent bundle to itself, this setting, such that this J star, J square is equal to negative identity. So then we call this pair M comma J is called the almost complex manifold, not the complex manifold yet. So there are sort of the distinctions in this level for the generalization, and because this is a seminar of the complex geometry, we will just clarify what is the complex structure. But this is a side like a remark. So there are two different like the directions of the generalization. One is the symplectic geometry. Symplectic word, they use almost complex structure for such as the mirror symmetry and so on. Mirror symmetry, infinite category. And in their framework, it's more natural to use the almost complex structure, but I will not talk about it that much for at least today, but this is their like the nature. And another direction is so-called the Sasakian geometry. Sasakian geometry. So also, I will not talk about the what is the definition of Sasakian manifold, but the examples are Heisenberg group, say from 2n plus 1 dimensional odd dimensional Heisenberg group to the R2n, or let me say 2n plus 1 dimensional odd dimensional sphere to the complex projective space. So this is also related to the complex geometry because CPN is the also model space of complex geometry, and real, let me say real hyperbolic space that maps to the complex hyperbolic space of the complex dimension n, so that if you just look at the horizontal distribution with the sub-Riemannian metric, then this will give you so-called the, so let me say for here. So different connection compared to the Leibniz-Civita, this is usually called by there are two famous terms of this connection, even though they are the same. So people in Sasakian geometry call this connection so-called the Tanaka-Webster connection. And from the community of the sub-Riemannian geometry, people call this connection by the both connection. They are actually the same. So this connection is metric connection. It satisfies the metric comparability, but not torsion free. The reason is that so they want to just look at the horizontal distribution, but not the vertical. That makes the distinction from the Levi-Civita connection. And still, the almost complex structure is generalized in a different like the manner compared to the usual complex structure in complex geometry. I think those two are also very important like the subjects. But if any of you have a request, then I would be very happy to also talk about those generalizations. But today, let's just talk about the complex structure. So let MJ be a almost complex manifold. So what we do is the following. So we start from take any point, so that we can create the tangent space as a real smooth manifold. We start from here. Then we'd like to make it to be indeed the complex manifold. So what we, in order to do it, is that so in order to introduce the imaginary number, then the way to do is just a tensor by the complex number. So that what we just simply do is just a tensor by C. That's all. So that if you just think, you already have the tangent vector, say x. So x usually represents the vector field, but because I specify this p, you can either interpret it as a tangent vector, or if you just remove this p, then it should be the local tangent vector if you want. Then the way to assign this guy should be just nothing but because we just make the tensor. So this is the natural choice. Just a tensor by just a one. So that we have this map. We have this map. And we didn't use the almost complex structure yet. So what we do is by using almost complex structure here, then we will decompose into two pieces. One is so-called the 1-0 part, direct sum with 0-1 part. So I need to explain what they are, but let me first explain how we map this element to here. So the expression is very funny. So we just split into two pieces. We already have x here. So from x, we just put imaginary number. Let me write as a square root of -1 and jx plus x plus imaginary number of jx. And now it depends on the convention. So when you read the reference, I usually take 1/2 for the scaling. But some of the reference take the square root of 2. There should be some freedom here for the scaling effect. And this guy belongs to here. This guy belongs to here. So the definition of this guy is that this is the eigen subspace of the imaginary number. And this is the eigen subspace of the negative imaginary number. Let me write that clearly. Minus imaginary number. So this is one of the invariant definition of the 1-0 part and 0-1 part because J is a linear endomorphism, so that we can just look at the eigenvalue given by either the plus minus I, then we can just take the corresponding subspaces in the tangent space level. And if you prefer the more like the concrete treatment, then this is just nothing but the C-span of DDZ1 to DDZN. And if you look at, so for example, so eventually I will simply just take the projection to mostly 1-0 part. And many people call without this P, so-called the holomorphic tangent bundle. Holomorphic tangent space because I fix P here so that we map this guy into here, then you can see that we should just map to 1/2 x minus I of jx. So for example, so if you just choose And this is already real 2n-dimensional manifold in order to make this J make sense because J square should be equal to negative identity in order to make sense to this like the condition, then this M must be even dimensional smooth, real smooth manifold for sure, so that you can just choose say x1 to xn and y1 to yn, and xi and y are related by the almost complex structure first, so that you can choose the local vector fields, say ddxi and dd, say, so let me use not I but j because I is somehow already used for the complex, the image number. So let me use index for j here. Then if you just use this condition here, then you know how to use the chain rule in complex analysis for the just a complex valued function. Then these elements maps to nothing but ddzi, ddzi. And if you map this guy, that maps to I of ddzi. So they are now linearly dependent over C. So ddxi and ddyi were not linearly dependent over real before for sure, but now we just make the tensor by C to make the complex vector space rather than the real vector space. Then ddxj and ddyj are no longer linearly independent on the holomorphic tangent space, so that the complex dimension becomes n, not 2n for sure. That's the reason. So that the T10M is the C-span of these local vector fields, and T10M is the C-span of, can you guess what they should be? With the complex conjugates. Complex conjugates, so that one of the real linear isomorphism is a complex conjugate. So that you can go from one to the other by simply just take the complex conjugate, just a bar. This is a real isomorphism. And you can easily check because we know what the description of this J. So for example, if you look at this guy, then you just use the definition of this guy like that. And if we already localize this complex structure, then you already know that this guy should be ddyj, and this guy should be negative ddxj. So by using this condition, you can check that this is equal to nothing but ddz. So it's just a calculation. I assume you know, right, for the rest of the you know how to verify. Is that okay with you? And similar for the like the complex conjugate part as well. So that now what we have is the following. So indeed, so if I just denote this guy by map here. So now we have a map from the original real tangent space to the now tangent space of the holomorphic tangent bundle that you usually denote by either the say well, either the 1,0 part or the holomorphic tangent bundle. So that we can now see from this construction, this must be R linear isomorphism. Because all we need to just count the numbers of the bases, and if the numbers are the same, then this clearly just R linear isomorphism for sure. But now we don't want to change the context. So what we want to do is we'd like to do differential geometry. So when we deal with the tangent bundle and the tangent spaces, we are not looking at the linear structure, say vector addition and the scalar multiplication, but we also deal with so-called the Lie bracket. Lie bracket is required to make our object to be so-called a tensor. Tensor means it satisfies the linearity with respect to the smooth functions. So in order to make that to be happen, for the level of the metric tensor and the Riemann curvature tensor, we must introduce the Lie bracket. So if we just change the object from here to here, preserving the linear structure, that's not sufficient. because we also need to transfer the Lie bracket from one to the other as well. But this constructor does not guarantee to preserving the Lie bracket structure. So that must be the definition of the complex structure that we can simply just now say, which is a theorem of the Nuremberg-Nilenburg. So I assume most of you already heard about it, and I just want to mention Nuremberg. So this condition is actually PDE condition. So we actually have a complex structure. Even I didn't define this yet because this is just a equivalence condition, so that you can take this as a definition. So this is a definition theorem. So actually it defines a complex structure, whatever complex structure is. So this means the following. So first condition, if X and Y belongs to the holomorphic tangent bundle, then Lie bracket should be also in the holomorphic tangent bundle. In general, there's no guarantee. This is a typical definition of the complex structure if this happens. And second, so one of the usual condition is the so-called the tensor n is equal to 0. So this tensor is a bit like the messy. So 2n times 2n, and it takes two vector fields, xy, then it is defined as a Lie bracket of jx and jy minus j of xy minus j of jxy minus j of x with jy. And this becomes tensor, and it is essentially vanished. So this is also one of the equivalent statement. And the second statement, so this is Nuremberg-Nilenburg, like the tensor. So why this condition was considered is that this gives the characterization of the complex structure. And this condition is very, very important in the deformation theory of complex algebraic geometry and so on, because this gives us the characterization. And another condition is that this looks weird. So the exterior derivative can be split into just the two pieces of the partial d and partial d bar. You might thought, well, this is just a trivial, so we can always do it in the level of the functions, but I'm not saying this is the level of the functions. This is for any differential forms. So in the any level of the degree k differential forms, we can always split the exterior derivative into two pieces. This is not free. So in order to guarantee this condition, because one need to deal with the complex structure, then this almost complex structure must be the complex structure. This is also another condition. And this is equivalent to say either partial composition of the partial D or composition of partial D bar or mix them must be essentially 0 in the level of the so-called Dolbeau chain complex. So that you also, I'm very familiar with this condition. So in order to create a Dolbeau complex chain complex, reasonably, then we actually need to look at the complex structure. Yeah, these are also the conditions for the complex structure. So before we move on to the next, like the condition, any questions or comments?
Is the statement of the theorem saying that each of these statements are equivalent to each other?
Yeah, they are equivalent. Yeah, sorry. So the followings are, yeah, thank you very much. Those followings are equivalent. But you can see the desire. All we want to do is we want to also guarantee that Lie bracket should be also preserved in the level of the holomorphic tangent bundle, not the real tangent bundle. This is not guaranteed because all we have is a linear, just an isomorphism. So the Lie bracket, there's no reason to get preserved. And if that's the case, we call it by the complex structure. So as a remark, by the way, for this open question, where was it? So in my best knowledge, I know that there are at least 3 almost complex structures on 6-dimensional sphere, but none of them are complex structure. There are complex, almost complex structures, but none of the non-complex, almost complex structures are not the complex structure, by the way. This is also one side remark. And also some side like the comment remark. This also actually good exercise, but still I'd like to give you some like the intuition. So given MG, complex manifold. So choose a local coordinate, say C1 to Cn. So this is our first line in complex differential geometry, and let F to be the holomorphic map. We know what is the holomorphic map. It just satisfies the Cauchy-Riemann equation for sure. Then in fact, this condition is actually if and if, because when we proceed the calculation, then we already choose the local coordinate. So this condition is same as that if you take the differential, because we can split this into two pieces as we know, we can do it so that we can take the Jacobian, then we can map with the complex structure induced from the just a complex plane. This is equal to, if I just choose, this is the original, I mean, this guy composed with the F. So if you just expand this condition with the local coordinate, then you can see that this is the way to glue the local complex structure defined over the actually Cn to the just a complex structure in the complex manifold. So if you just use the Jacobian matrix, then you can see very clearly. And this condition is just actually Cauchy-Riemann. So, but anyhow, intuition is somewhat clear. Right. So if there are no comments, then let me move to the second object. What is it? So it's about the but I today want to talk about the Kahlerness. And because this is the learning seminar, so I don't try to spend all this time for my own presentation as a lecture style. I also want you to like look at some detail and you can also present. I think this is also one of the good, like the part that, so if you are ambitious to study complex geometry, I actually highly recommend you to uh, do the following. For the rest of today's like the seminar, I want to just mention about the statement written very clearly with the proof over here. And in this reference, I think this is one of the best reference so that you can look at here. You can look at here. And I'd like to jump into one of the proposition in chapter 4. Let me show you. And I invite you to present the detail for your own learning purpose, that this is very helpful. So first, this is a statement today I want to mention. So theorem 4.17. So we have a complex manifold with the comparable Riemannian metric. I will mention what this condition is, and also Levi-Civita connection. Then they are all equivalent. So now we care whether or not the given Riemannian metric becomes the Kahler metric. This is a condition we'd like to care. And there are several conditions. Either this omega that we need to define. Omega, if you take the exterior derivative, it becomes 0. And this J complex structure is already given. If we take the covariant derivative, it's equals to 0. This condition is also extremely useful when we proceed the calculation. And all other conditions are very important. Say Chern connection coincide with the Levi-Civita connection. And this condition it actually is actually the so-called holomorphic normal coordinate. If you already know the normal coordinate from Riemannian geometry, this means that actually we can take the holomorphic normal coordinate. And this condition also extremely important when we talk about polaris of harmonic function for the potential one, so that we can always represent the Kahler metric as a complex Hessian of some potential function. This condition is extremely important. And the Bergman-Kahner and the Bergman matrix, one of such like the example. Then in the case of bounded domain, we can take such a like function globally. At least in the case of the bounded domain. And this is also the holomorphic normal coordinate condition, with sort of similar to the Euclidean metric. And there are the proofs here. There are the proofs here, even though it's written in short, but this is very important detail in my opinion. And in order to follow this, like the details, then one first need to look at this identity. Let me, so I will go back to my note to write something, but still I'd like to mention which types of the detail would be required. So this, you can just assume this omega is a differential two form. that we'd like to define. So let's just assume you already have a differential 2 form. Then after taking the exterior derivative, then this becomes differential 3 form. So it makes sense to take 3 vector fields for sure. But as far as we know, for the level of the 0 form and the 1 form, say f is the function, and if we take df, we know what the definition of df. Is that okay with you? Df just means that we take each partial derivatives and we just put dxi. That's it. But when we start from the differential 2 form here and create the differential 3 form, and if we really want to proceed a calculation, then if you look at the right-hand side, this looks quite non-trivial. This looks quite non-trivial. And in order to understand this identity is coming from the slight different perspective from Riemannian geometry. So let me show you that formula. So this is what exactly you need to study. If you want to catch up the details of this equivalent statement, then this theorem requires this guy, which is this part, and this requires understanding of the first identity here. Is that okay with you? So first identity here, and this first identity is coming from the following. So I just let me also share another website, and then I will go back to my note. So if you search fundamental theorem of Riemannian geometry, and these two conditions characterize so-called Levi-Civita connection. And if you never studied the Riemannian geometry, in that case, let me know. I'm very happy to present the details to introduce those like the object intuitively. But for the usual line of learning the Riemannian geometry is that by using them, then they use so-called the local coordinate to write down the crystal symbol in terms of the local coordinate uniquely. That's what the students in Riemannian geometry, like the class, are usually learning. However, these are what the people who already took Riemannian geometry class already know, so as a known formula for sure, but the line is slightly different. So this is what we need, so-called the causal formula. So rather than taking so-called local coordinate to drive the expression of the crystal symbol, so this is the expression of the without the local coordinate. So this is a equivalent statement to drive the CRISPR symbol condition based on the condition Levi-Civita connection. And you see that this is two tensor. These are two tensor, and we have a coordinate-free expression to represent this left-hand side. And by combining the definition of omega with this so-called causal formula, then one will recover that expression. I mean, so that this expression is in fact, they're a consequence of the causal formula. So that the way to study is that you first look at the characterization of the Levi-Civita connection, and rather than going to the coordinate expression, but you need to choose the coordinate-free expression that's called by the causal formula. And by combining with the definition of omega, then one will get this. But the details are a bit tedious, so that I'm very happy to look at the detail together, but if someone want to just write down the note line by line and present, that's the purpose of this informal seminar, so that you can do so. And this is very important, like the detail, to understand these details. And because the complex structure has a lots of the variation in either symplectic geometry, Sasakian geometry, and so on. So that's why I invite you to look at the detail if you are interested in, and if you have time and energy. But so I just today want to introduce the definition of this omega. Is that okay with you? So what I'm now doing. And you can just also search this like the reference from Google. I think you can find the PDF file. And if you cannot find it, send me the email. I'll also send this file to you. All right, then let me go back to my note. So one of the most like the preferred description of the Kahler metric is so-called written as a so-called symplectic form. So we start from complex manifold now. So now we have a pair. Be a complex manifold. So that we already assume this J is complex structure at this point. It satisfies all these conditions here. Is that okay with you? So these are already given. So I'd like to say this, so let me just copy we already saw. So we have a Riemannian metric on M, or you can just assume Tm tensor Tm if you want, because it's a actually two tensor, but usually we just equip with the Riemannian manifold such that what we saw is this J is compatible with J. This is what we saw from the statement. This condition just means the following. So i.e., so if you plug in arbitrary vector fields, local vector fields that are defined, this is same as G of Jx with Jx. Sorry, Jy for arbitrary like the sections of the tangent bundle. This is the condition of the comparability with the complex structure. You can simply say this condition just means J is a Hermitian metric. That's all. So the Hermitian metric is a special Riemannian metric with having the comparability with the complex structure. So that you can kind of intuitively just interpret this J behave as an orthogonal transformation if you want. Because J square is a negative identity. So if you plug in J one more time, then you can get negative X and negative Y and so on. And we already have Levi-Civita connection. So that we can apply the causal formula as I already showed you. So what we do is up to here, we treat everything as a real object, not over C. We so far treat everything over real. So that what we want to do is we'd like to complexify everything at this stage. So what we do is we extend, for example, J, for example, metric, Hermitian metric, the Levi-Civita connection, or they as a C linear way to extend. So please do not get confused that, for example, this V local, like the section or the local vector field was a real vector field, but we just want to multiply by any complex number at this point. Then we extend this C linear way so that this must be alpha of J of V. For example, for arbitrary alpha in B, and with the same reason. So if we have the X and Y for the Levi-Civita connection, then we also will multiply by any complex numbers, alpha and beta. Then it does not mean that we look at the complex conjugate, we indeed just take to be just alpha beta without the complex conjugate, like that. And this part could be confusing. So if we also plug in X and Y, so we're okay with it. However, we will also multiply by the complex numbers, alpha and beta. You might feel, well, for this beta, we need to put the complex conjugate. No, we just take the C linear way so that this is equal alpha beta G of xy, not beta bar. This is caution. So this is not beta bar. We're still dealing with the real objects and we just extend C linearly. Is that okay with you? So this is our starting line because so far everything was just a real Riemannian manifold. Some of the special real Riemannian manifold. Then what you can now see is the following. Then, so let us just choose near point P. So we have a C-span of the DDZ1 to DDZN and DDZ1 bar to DDZN bar. So this just creates the complexified tangent bundle. Not just a 1-0 part and also 0-1 part, we take the direct sum again together because we also have the complex conjugate like the part as well. So that we can plug in all those bases into the Hermitian metric because Hermitian metric takes any complex like the extension of the vector fields so that if you, for example, choose the same type like that, because this is just nothing but a complexified vector fields, then by using the Hermitian condition, you can see that you should get this. Because this is what we require as a Hermitian condition. Then what we know is that, so these bases are the eigenvectors with eigenvalues is given by imaginary number, so that you will see that this is nothing but this guy. This guy. So that now you should just take this without the complex conjugate. without the complex conjugate, then it's just nothing but multiplying two imaginary numbers, then you will get negative g of this guy. Then you can now say the consequence, it must be 0. There's no other choice. So that if you plug in same types of the vector fields, with this reasoning, you always extract the -1, so it must be 0. So similarly, you can expect that if you now plug in section from 0, 1 part. So now I put the complex conjugate for each, then with the same reasoning, you will get 0. So all things survive is just nothing but G, so-called DDZI with DDZJ complex conjugate here. So make sure that now we can see why we need to put one part to with the complex conjugate. This is in general not 0. So that it makes sense to talk about the complexified two tensor Gij bar. So this is denoted by Gij bar in general. And we just put DZI tensor DGJ bar. And I omit the notation of the summation. So you should assume this is a convention from differential geometry that if we have a two repeated indices, then there is a summation always. So two i's, two j's, so they are taking the summations. That's the convention as a two tensor. And you can see that this Gij bar, even I already mentioned, this is defined as a local smooth function in this way. And you can also check that if you just switch those two, but we put the complex conjugate in the second, like the slot, and in that case, you can check that you just need to put the complex conjugate here. So this is the condition that you can just check by just writing everything. So that this is the same as a so-called G, Ji bar with the complex conjugate, like that. So this is, here we use the Hermitian condition. Now we are ready to introduce omega. This omega defined. So some of the reference call this omega by the Kahler form, even though the metric might not be Kahler. So I time to time feel confusing on it. So let me call it by the fundamental form. So this omega is defined as a G of J here and here. This is a definition. This is definition. And in a local coordinate, this omega is defined as a I of Gij bar with DZI wedge with DGJ bar. So you can check. So these are good exercises. I'm very happy to also do it with you, but exercises that you can first check that omega of xy is no longer equal to omega of yx, but you need to take the negative sign because you know that j square is equal to -1, and by using the Hermitian condition, you can check that. And if you put this imaginary number is coming from the following identity. I is equal to I bar. So this is the so-called real differential form. And each of the components are indeed given by Gij bar. If you just think about this definition, this is already actually clear. So many people also call this by just a matrix. But in the world of the complex, like the geometry, so we prefer to denote the metric not as a two tensor, but as a fundamental two form. So that fundamental two form also encodes all information of the Hermitian metric or the Riemannian metric. So the Riemannian metric can be represented by this fundamental two form omega. So now we have a definition. Given M, smooth manifold, J, complex structure, this guy, and G. So all those objects that we mentioned, we say omega is Kahler, if the omega is essentially zero. And we saw the equivalent, like the characterizations of this algebraic condition, what it actually represents. So I think today we can simply just finish over here. And from next time, with starting from this, like this setting. So again, this M just represents the smooth manifold, J stands for the complex structure. This connection, the nabla, is actually the Chern connection, truth be told. Chern connection, not the Lebesgue-Witten, but so we already used actually the Kahler condition somehow, and this dream is the Hermitian metric. So we have the condition of the Navier-Kahler metric. Then now we are ready to understand this Calabi conjecture. So, and in order to do it, so this condition related so-called the Leach curvature. So I need to explain what the Leach curvature is, so that if you are like interested in learning like this subject, then there are two things to track together. One is in the case of the real surface, Gaussian curvature equals the Leach curvature, so that you can just first like look at the calculation of the Gaussian curvature in the beginning, and given the Riemann metric, then you can also check how to proceed the calculation of the Leach curvature in the local coordinate, and we will simply just take the complex, like the complex 5D calculation, and take the Leach, like the tensor, as also differential 2 form, and then we will just look at the details together. So if there are no comments, then let me stop to record over here.